I'll just quickly introduce myself before we get into the topic. So, as already mentioned, I'm an embedded engineer. We're around 11 years of experience so far. I'm working and have been working in Sulky engineering for the last 4.5 years. I come from the mathematical computer science background from the Faculty of Mathematics in Belgrade. And my main interests are in mostly related to embedded, but also other topics such as Linux as the operating system, C, because it's, as I joked here, effectively a macro assembly, but you can run it literally everywhere. Modern C++, which is mostly the topic of this talk. And of course, Haskell, which is, let's say, my hidden love, but in embedded world, it simply won't land anywhere soon to some real project. Okay, so why are we discussing physical units at all? Embedded devices interact with the real world, and by its nature, we will either collect or emit physical values, be that length, speed, mass, acceleration, electrical current, or any other physical unit you can think of. We need to deal with those. Now, there are some inherent issues, and we will not deal with all of them. But for example, the precision of measurement, usually it relies heavily on the hardware quality of the ADC circuit. The speed of acquiring measurement, again, the hardware issue and usually in direct opposition with the precision. Precision of calculation, this is a common problem where we may lose some precision with the or some of the data during multiplications, divisions, and so on. But these are all covered either by hardware or specialized libraries. Today, we will deal with the consistency of units, so hidden devil of the field. So, how did we deal with that in the past? We would usually mark the value, such as mass in kilograms or mass in pounds, mass in ounces, volume in milliliters, in centimeters cubed, or again in ounces, whoever likes imperial system. And the problem there is that nobody's forbidding you from adding mass to electric current. Those are just numbers. Again, mass can be expressed in many different ways. Even within the metrical system, it could be milligram, gram, or kilogram. In the imperial system, it could be pounds, imperial tons, ounces, and many, many other. Now, we can add conversion functions for every possible combination, but first of all, we need to verify that each combination is legitimate and that we are using it in appropriate place. Now, the best solution, theoretically, at least from my point, would be that the physical unit checking should be somehow part of the compiler, or we should force the compiler to do all the dirty work for us. So in the optimum case, if we try to add milliliters to meters, we will simply get a compilation error, which is much better than a runtime error by an order of magnitude. So let's first introduce the playing field. Whoever let's say, has read any historical novel or anything from more than 100 or 200 years ago will definitely know that there were not one or two, but there were many different systems of measurements, mostly pertaining to the length, surface, volume, mass, but there are also others for time and temperature. And after a while, we reached the International System of Units, or the SI system, which is currently completely predominant, with only 3 countries in the world still using imperial system by default. That will be USA, Liberia, and Myanmar. With USA being such a huge economical and political powerhouse, we do still need to support imperial system in many of our applications. Now, the SI system made a system of measurements which is far more profound than having everything as a multiply of 10 or 100. We have 7 basic units: ampere, Kelvin, second, meter, kilogram, candela, and mole, expressing the 7 basic, we will call it in this talk, dimensions of physical reality as observed so far. And every other standard unit can be expressed through some combination of those 7. With example given here, a volt. Nobody will probably write down the volt as kilogram meter squared over second cube and ampere multiplied, but in reality, this is what volt is. Non-SI units can also be expressed through various calculations. For example, Fahrenheit has this relation to Kelvin. Now, why did I ever started resolving these sort of issues? Well, there was a real life project, of course, in Zülke, and the device that we were working on was mainly used for heating up the water, such as tea preparation or coffee preparation and such. Some of you may ask, why didn't we use some of the existing libraries for physical units? But there were actually 2 drivers. One was that at that stage of the project, no additional third-party software could be added due to some licensing and legal restrictions, which were simply beyond us. The second issue was that this being an embedded device, a majority of calculations should be done in signed integers and not in floats or doubles, which are the standard for majority of physical unit libraries. At that point, I tried to analyze what we have there, what is currently being used in the system, and how can we consolidate the physical units. So there was quite a lot of usage of time, hours, seconds, and milliseconds. Majority of that was actually used by the operating system, but still a substantial part was used in the business logic. Volume, of course, we were dealing with water. Temperature was measured, interestingly enough, in both Celsius and Kelvin. And there were many other interesting units, such as frequency, various electrical units in like amperes, volts, ohms, flow in milliliters per second, and so on. Ideally, the solution that I had to propose needed to have 0 or very small runtime overhead in all possible aspects, since we were very low on the available memory already, and we didn't want to jeopardize the real-time performance of the system. Also, a good bonus would be if the code refactoring could eliminate not all present inconsistencies, but if it should make all future inconsistencies simply impossible. Bonus there was that if the code could be more readable and aesthetically pleasing for people doing the code reviews, that would be very nice. Okay. So a great benefit was that the project was using C++ 14. So we were already in a very good place. We didn't have to negotiate with the client. In many other projects and cases, we had to. And what was the benefit? Now, majority of you know that the C++ 11, 14, 17, and so on brought quite a lot with them, and that actually the majority of the innovations were not so much in the object-oriented part of the language, but much more in the generic and functional part. So we will focus on some of the new features and new options we have in the language, which made this solution possible. First and foremost, it was actually template programming and const expressions, which could be used now in methods, functions, and so on, that allowed us to have all the type checks and conversions done in compile time. When I say type checks, you will see how we tricked C++ or made it so that the dimensionality analysis. So is something a length, a surface, a volume, electrical current, or a voltage? Whether we force C++ to treat those as types. Therefore, template programming helped us a lot. Suffix operators, which were introduced and are used very nicely in STD Chrono, can also now be used for physical units too. So we could have 10 milliseconds, 14 liters, and so on. As for the conversion factors and the dimensions, STD ratio, which was added to modern C++, also proved to be extremely useful, given the fact that it will make all the conversion functions and all the factors for it in the compile time instead of the runtime. We also try to focus on to distinguish between absolute and relative values, similar to what has been done in Chrono Library. So we will discuss this in more detail when we reach that point. Okay, so how did I start? So the basic physical unit, as you can see here, I hope that people can see the cursor. We have the value type, the factor, and then the 7 SI units in the class physical unit. So a value type can actually be an integer, unsigned or signed, 16, 32, 40, 64, whatever you like, float double, long double, and I was even asked if it could be a complex number. Honestly, probably yes. I just didn't have a chance of using that. Factor was set to STD ratio, so we allow by this the units of the same dimensionalities but different scales, such as liters, milliliters, meters, kilometers, millimeters, and so on. The basic unit to which all will align is always the basic SI unit. So we will always express volume effectively as meters cubed, with, for example, 1 liter being the 1,000th part of a meter cube. So whatever we do, our anchor will be the 7 basic SI units. Now, the 7 dimensions could have been integers for the entire presentation and what we did, but I introduced STD ratios there too as a better and future-proof solution, so we could support potentially fractional dimensions such as square roots and other edge cases. Okay, so that was the ground foundation, how I started. So one of the first things which was interesting for me was conversion constructor, and you can see here that it is quite easy to do, because we will keep the 7 dimensions as they were. The value type may change, and of course the fraction may change. So we could very easily, by picking up the ratio numerator and denominator, we could very easily do compile time conversions of one physical unit into another if the dimensions check out. Now, some of the prudent people among you may ask why the explicit keyword. Well, this can be done much more elegantly and implicitly. Quite a few errors that we had were due to the implicit nature of using just raw floats or double floats or integers or unsigned integers in the code. So we could accidentally add milliseconds to seconds or seconds to milliseconds, and that was not, in that part of the code, the actual intention. It was just the programmer's human error. So the explicit keyword assures that we will not have any of these accidental conversions, which may ruin our day. Let's continue on. As for the comparisons, if this was done now with some compiler supporting C++20 spaceship operator, this could have been much more concise and elegant. But for every comparison, I had to write 6 operators, so equality, non-equality, lesser, greater, less equal, greater, equal. And these are, as you see, quite simple. In the first version, I actually enumerated here all the dimensions for the first physical and second physical units, and the factors too. But then it came to me that actually the variadic templates make my job and life much easier and future-proof, because we are implicitly saying here, outside of these value types, everything else in these two physical units must align perfectly. I will not test for equality between milliseconds and seconds. You must first do the conversion on one way or the other. I won't try to figure out what you wanted there. So also, if we would ever make the physical units more complex, for example, by adding additional 8th or 9th physical unit, this code will simply check out, because the variadic templates give us that. Now we'll first begin with the simpler arithmetic operations, such as addition and subtraction, and move on to multiplication and division, with division, of course, being the most complex. So you see here that if you compare this snippet of code with the comparison piece of the code, it's very similar in the sense that only the types of V1 and V2 for the physical unit 1 and physical unit 2, or the left and right side, are different, and the factors and the dimensions must check out perfectly. But there is additional bonus from the modern C++. The return type will be decided at compile time. So of course, whoever is knowledgeable in this area, this won't be a surprise. But for those who see it either for the first time, or they had a longer pause of not seeing this, C++ allows us to have the return type, so this value which we have here, V1, V2, as something which can infer from the addition. Now, what does that mean? So I don't want to confuse anybody. In standard C or C++, if we would add an integer to a float, there is a known, I'd say, superiority table, if I can call it like that C or C++ compiler could detect that integer and floats are different primitive types, and the integer should be cast into float before addition happens. So we will have the float as the actual result type of this addition. We would like to have the same feature for our physical units library. So if for any reason somebody calculated mass in integers and another place in floats, if we add these two masses, we will get mass in floats. So let's say, in my opinion, what we actually expect a compiler or a library to do. This decl type allows us to do that. So we can proceed. Now, multiplication and division is, of course, more interesting, and there are three parts to this. First and foremost, we will deal with scalars. So multiplying with a scalar from the left or the right-hand side is quite easy. Dividing a number with a scalar, also quite easy. And you see here that the code is not particularly challenging. And the type is again inferred. So if we multiply an integer physical unit with a 2.5, we will get a floating point or a double, or whichever the type was for the literal. So it's still now quite similar to the addition and subtraction, with some new addition here. And let's move on into a more difficult situation. Sorry. Okay. The more complicated and convoluted situation is when we would like to divide the scalar with R value. So, for example, we want to divide number 1.0 with 10 seconds. This would give us a frequency now, because a second inverted is actually a frequency here. We will get hertz. Now, we wouldn't like to lose the values. So the milliseconds here or seconds are given as integers or of 32 or 64 bits. But what we divide here is a float or a double. We would like to stay there. Now, several things will happen. The decal type part, you shouldn't be surprised with that now anymore. That's an easy thing. But in comes a more interesting part. The factor is actually now the inverse of the factor that we had. So if we had a millisecond, if we divided anything by millisecond, it would actually now be what we divided here, not 1,000th part of a second, but 1,000th of what we are dealing with. And all of the dimensions will now be there, let's say, subtracted from 0. So what we will have here, if the time dimension was 1, we will have a -1 here. If something was 2, we will have a -2, or vice versa. If we divided something with the frequency, which had a negative time, -1, it will now become +1. Okay, so the inferring of the return type is here a bit more complex. I will leave a few seconds for everyone to, let's say, to grasp this. But as you can see, the pattern repeats from the previous slides, but actually we now started dealing with the inferring of the dimensions too. Now we will proceed to the third part. And now, if we multiply two physical units or divide one physical unit with another, we finally reach the most interesting and complete case of working with the physical units. Now, interesting thing, you did see previously that when we add, subtract, and compare, dimensions have to check out completely. Multiplication and division are actually completely free from this consistency. But on the other hand, we need to do complete inferring of the types. So if we focus here on simple multiplication of these two physical units, you will see that the multiplication is again done with decal type, so we can infer what's going on there. We will now multiply the factors because we're multiplying here. If we did the division, it would be the other way around. We will now add the dimensions. If we did the division, it would be subtraction. And again, we will, in the end, just multiply the values. So this is, in the end, if you follow through this build-up, there is a common pattern, and we just add another more layer of complexity here to reach our goal of valid multiplication and division of physical units while maintaining the proper types, factors, and in the end, of course, the prime motivation for this talk, the dimensions, physical dimensions. Now, in many occasions, you will actually reach the point where you want to treat the physical unit, resulting physical unit from some multiplication or division, as a scalar. Now, this is perfectly fine if we divided kilometers with meters or multiply time with frequency. We will actually reach a dimensionless value. So the value where every single dimension is 0. So here, of course, this is not legal code. This is not ellipsis in the real code. You would put STD ratio 007 times. But what's interesting here, with a simple template specialization, we introduce that we can have a val type, as I called it here. It could have been something more aesthetically pleasing. But we can extract the complete value outside of a physical value and do calculations with it, as it is now free of any dimension. So we can treat it as a normal number. Okay. Now that we covered the entirety of relative physical units, we would like also to delve in the absolute physical units part. So some physical units that we measure are measured from a specific point, such as time, So let's put it this way. If we say that this presentation will last for an hour, the same hour can be applied as a length of any presentation for this day or day before without any issue. Now, when is this happening? We need a reference point, be that 1st of January 1970, 1st of January of the number of the year 1 AD, some other moment in history. It's completely irrelevant which one you choose, but you do need an anchor. For the relative values, you actually don't need any anchor whatsoever. We also saw that quite a lot in our code, that the temperature also deals with this, in the sense that we may measure the temperature of the liquid, but we also sometimes want to calculate the power needed for heating some particular liquid by 20 degrees more, or to cool it by 20 degrees. This 20 degrees here is not 20 degrees of Kelvin or Celsius in the sense of 20 degrees above absolute zero or our water-based zero. This is a difference. And we needed a way to express that in the code. So absolute units actually share quite a lot with the relative physical units, but there are some prime differences. If we subtract two absolute points, we will get an interval or a relative value. Adding or subtracting an interval or relative physical unit from an absolute unit will lead to another absolute unit. Comparisons will work the same, and no multiplications or divisions could be allowed for the absolute units, in the sense that we may reach a point where we want to multiply seconds by seconds. That's fine in physics, but multiplying dates by dates, for example, the date and time for this particular moment when I'm speaking, probably has no applicability in physics, and we simply won't allow that. So let's look at here. You may see that the prime difference here, and the only difference in the signature of the type, is the difference type. Now, why we wanted to have that? In our code, at least, and because it's an embedded device, we wanted to save as much space as we can. For example, all the absolute time points were calculated as milliseconds from the beginning of the Unix era, and these had to be in 64 bits. But the time intervals that we needed in the code for milliseconds were definitely in the sub 32-bit range. So we wanted to have relative units in 32 bits to save both space and the CPU cycles. Okay, let's continue on. Now, subtracting two absolute units, as already mentioned, quite easy. We need to have two same absolute units, and we will return a differential physical unit just by and take the values of these absolute units and subtract them. This is quite easy, actually, given the fact that the entire complexity of alignment of the dimensions and factors is done by the templates themselves. Now, when we want to add an absolute unit and a relative unit or a normal unit, or subtract, you will see here again a very nice usage of the variadic templates, where we take that the difference type here and the difference type of the physical unit must align. In some expanded version of this, we could also theoretically go for inference of the types, but for our code, it was deemed more, let's say, this would be an expected behavior. Let's put it this way. Let's go on. Now, let's focus a bit on how to create specific units. We will do an example of the volume. Volume is we want to express it in our code in liters or milliliters because we're dealing with liquids and these are natural there, but they're effectively 10 to a minus 3 of the meters cubed. So let's see here. Liter is a physical unit expressed as a float. This STD milli is from the STD ratios. It's already being used in STD chrono, and it's part of the C++, modern C++, so it's nice to have it there. As you can see, length is on the third degree. All other dimensions are set to 0. This is only to define a liter. Now, I would also like to use liter in this manner: 10 liters or 3.5 liters, and so on. And here we use the suffix operators. They accept, in our case, the uint64 and long double as the literal values. And there we would finally call the constructor of the liter with the proper conversion in the underlying type. Now, to repeat again, every derived unit is only expressed as a combination of the base unit with the corresponding conversion factor. Any more complex conversion, which is usually, from my understanding, when we deal with the imperial units, such as kx plus n, in the sense of Fahrenheit to Celsius or Fahrenheit to Kelvins, was not covered here, as it was deemed not necessary. We didn't use any such unit such as Fahrenheit, and it would dramatically increase the complexity of the of many of the arithmetic operations, such as multiplication and division. So let's move towards the summary. Now, what did I learn here? First of all, compared to what I learned at faculty, templates are getting really, really powerful and can be used to statically resolve issues in compile time, which we would usually pay dearly in the runtime for some library to check the types, dimensions, and all of that, and introduce, in our case, unnecessary cost and penalty for the runtime execution. Suffixes were very welcome, at least from my colleagues, because it was very easy to understand what we're doing just by looking at the code, because quite a lot of constants were used in the code directly without assigning them to any variable, and that was really nice to have. This inspired quite a bit of work on my part in some other projects to push not only the physical units, but that was the prime motivation, at least for me, in several embedded projects, as physical units are used all around, but also for other checks that could be done in the compile time, contrary to the runtime checks. Also, let's say a personal life lesson for me was that I was actually, in the beginning of this challenge, very annoyed that I cannot use any of the existing libraries, but in the end it proved to be a really good learning experience, and I'm very glad that I had that impediment in front of myself. Things that were lacking in this code, and I was notified by others who actually were looking into the topic, the creation of types is actually not that nice. It could be made easier. Another thing is that the cloud part of the IoT projects, which were mostly currently written in C#, Java, and other enterprise languages, they could use the benefit of this approach, or this library, a similar library, in the sense that it is also dealing with telemetry data, which are physical units, and there are some calculations and whatnot on the cloud side, which could also benefit from these compile time checks. A thing which was asked very early from one colleague of mine was, how would you express an angle? Because effectively, angle is a dimensionless value of division of dividing a length by length, but it's not simply a value. Now, in all honesty, there are two approaches. I mentioned here one in writing, but there is a more consistent one. One approach, what I've seen people doing, is introduction of the 8th dimension, and then you only need to deal in some specific cases when you convert and multiply and divide lengths and angles. You need some special code there, and it can serve the purpose. What's actually completely missing from the solution here, and it's a let's say, a good invitation for the audience to maybe test their wit. We actually have several kinds of same values, and when we reach the dimensionless values, such as the angle, what we have there is we have a kind of something. Also, we could have issues when we deal with 3D or 2D data that are length on the x-axis and the y-axis are lengths, but their kind is different. Adding them would create a vector. Adding them would not be a simply 3 plus 2 equals 5. For this sort of dimensionality analysis, where we could have potentially infinite amount of dimensions on any of these, or that we could have different kinds of energy, like electrical, kinetic energy, or thermal energy. That was for me, when I came to the conclusion that this is not covered, that was an order of magnitude more complex than I was willing to spend my time. And as a clear embedded engineer, this solution was definitely good enough for what we did in the project, and I stopped with the development once this was complete. So these are some open points and interesting points, and I know that there are teams across the internet which are trying to deal with these sort of issues and push them also in the compile time. Some of them are even proposing new features in C++ 2023 that should make this work possible. That would be mostly it. Thank you for attending. I will now be open for questions from the audience.
Yes, hello, welcome back. Thanks for the audience for coming up with questions. And I just start right away with the first questions. Maybe this was covered in like some of your last sentences where you talked about kinds. Someone asks, what about same units that still cannot be added to one another? Like they would know for a fact that specific thrust on rockets is measured in seconds, but this has actually no real relation to a time span, or simply a height of a car that is not the same as a distance of a route it might travel. Would it be easy to just annotate these kinds to just forbid this, to just say, okay, I have that extra string, whatever, that I just say, okay, these do not match because this extra type is in place. And
if we would only have these sort of kinds in between an annotation, probably yes. But when you reach the problem that I mentioned, for example, a three-dimensional situation where we have x, y, and z axis, and you want to have, for example, in these physical units, God forbid, a rotation of sorts, then we enter the field of not only having kinds, but maybe even some sort of matrix representation of dimensions and so on. That was out of scope. I would definitely go, if I had to introduce kinds, in only annotating a single kind, like no kind at all, and then 2, 3, or 4 kinds that we would use in the code. That would probably be somewhere in the beginning, so either before or after the factor, but before the dimensions. I wouldn't like that to go along with the dimensions there. So that would be a simple extension. And as you all saw, because of the usage of the variadic templates, we would probably get away with that. Now, what would we do if we want to multiply something which has one kind and something which has a different kind? That would be probably a different question. As I said, it's a deep rabbit hole to cover.
Okay, we have another question.
Yes?
Someone's asking, once you were on it, could you also cover uninitialized values with your framework easily? Would it be easy to add that?
Uninitialized values, sorry.
Yes, like a kilometer range or something like that, where you really wouldn't give a value to it, but the variable would exist.
Well, if we would create such a thing, okay, yes, I didn't include that. So there is like an empty constructor which will just give you a 0, of course.
Okay.
If you create something which is of type kilometers, for example, it will just have 0 kilometers, whichever, of course, arithmetic value you choose to have there, be it an int, float, or whatever.
Someone else asks, would this, what you've shown, also benefit from const expression in your real-world projects? The way you use this library?
Yes, well, all of the methods were const expressions. So, for example, if you did have an interesting computation where actually only had one variable, everything else would have been, because it's a literal or a constant there, and because these methods are const expr, you would get quite a lot of benefit there. So I either failed to notify that in the code. Sorry for that, but the question is on point. Const expressions are very useful here.
Okay, there's one comment, and maybe you can just also comment on that. Someone saying you should also mention boost units, which is basically the same and ready to use, or do you disagree with that and you checked it out and just didn't see it fitting for your case?
Well, boost units was actually the first thing that I found, and then we came to the licensing issues. And there, the problem, one part of the problem was this. The other problem is enforcing of the type. Boost units, as much as I try to find out how they work internally, are mostly focused on using, let's say, doubles or long doubles. And this shenanigans that we did, that we are trying to, for example, keep certain calculations within integers and only convert to float one only necessary, I didn't see that supported that much in Boost. So for embedded target, a solution which is much more sensitive about the underlying type would be, let's say, would be better, would be what we would expect there. And the Boost is definitely much more feature complete in many aspects, but those were the two reasons not to use it. One was licensing, which was a dead showstopper. The other thing is that enforcing long doubles or doubles across our code was something that would significantly impact the throughput power of our CPU. We couldn't do all the calculations then in the appropriate time slots. I hope that this covers the comment.
Okay, maybe the last question. Did you write a nice printing method for the combined or more complex units just for a debug output or something like that in a nice way, such that I see the formula of units that is created when multiplying different kinds of units?
Well, no, but there was actually a silly reason not to. Nothing compiled if the units didn't align. So what I did have there is usually that the compiler would complain that the units won't align, and then it would print out what was one template, what was the other. So we never reached the situation of having a code in runtime where we do not know the units. So no, it was not there, but it should be relatively easy to cover. I could also imagine a really diligent person finding the most common combination of dimensions and already trying to condense them, like I showed for
like
Volt
in a dictionary or something like that.
Yeah, but again, that was too much effort, and literally none of the developers in the project wanted to have that because, as I said, code wouldn't simply compile if the units were misaligned.